A gas occupies a volume of 4 liters at a pressure of 2 atms or atmospheres. And if the volumes decrease to 2 liters while keeping the temperature constant, what will be the new pressure? Let's write out what we're given. We're given that our volume is starting out at 4 liters, and our pressure is 2 atms. Now, our volume changes to 2 liters, and we're trying to solve for the pressure. So let's call it X. And our temperature is constant, so we don't have to worry about using a formula that involves temperature. Now, based on what we're given, what formula do you think we're going to use? Well, we're going to use Boyle's law, which is P1 times V1. No, sorry. I don't know why I wrote 2. P1 times V1 equals P2 times V2. Now, let's use this. Plugging this into our equation, we're going to get 2 atms times our 4 liters equals to our unknown, the thing we're trying to solve, which is the X. And this is going to be multiplied by our V2, which is 2 liters. Dividing 2 liters on both sides, this cancels out, and we can cancel the liters out. And we're going to get X equals, so far, if we solve this further, we're going to get 2 atms times 4 equals to 2. The 2's will cancel out, and we're going to get 4 times this, which is just 4 atms. And because everything has one significant digit, our answer is valid. So always make sure to check in these types of problems that you rounded to the correct number of sigdigs. And in this case, we have a gas at a temperature of 27 degrees Celsius occupies a volume of 2 liters. If the temperature is increased to 127 degrees Celsius, while keeping the pressure constant, what will be the new volume? Because our pressure is constant, we know that we're not going to use a formula for this. Our initial temperature is 27 degrees Celsius, and it occupies a volume of 2 liters. Now, we increase the temperature, increase the temperature to 127 degrees Celsius. And we want to find out what our volume is. Now, based on this, what formula do you think we're going to use? We have temperature and volume. Therefore, we're going to use Charles's law. V1 divided by T1 equals V2 divided by T2. But wait, this formula only works if our temperature is in Kelvin. And right now, our temperature is in degrees Celsius. So let's fix that. So our T1, let's convert this into Kelvin. Add 273 degrees to it. Or 273, I'm sorry. And we're going to get 300 degrees Kelvin. So this is going to be our new T1, you can think about it. And our T2, 127 plus 273, well, that's going to get us 400 degrees Kelvin. So our kind of revised kind of equation is 300. We have 300 degrees Kelvin for our T1 and 400 degrees Kelvin for our T2. Plugging this into our equation, we get 2 liters divided by 300 degrees Kelvin, and this is going to be equal to X divided by 400 degrees Kelvin. Cross multiply, and we're going to get 300 degrees Kelvin times X equals 400 degrees Kelvin times 2 liters. Divide both sides by 300 degrees Kelvin. And since the kelvins cancel out, we're left with liters. And because we're trying to find the new volume, this is correct. we're going down the correct path. And we're going to get x equals, so 2 times 400, that is 800 liters divided by 300. The zeros, you can think about it, the zeros kind of cancel out. We're going to be left with 8 divided by 3 liters. And 8 divided by 3, that's just going to be 2.666 and repeating, but liters. But we have to round to the correct number of sig digs. The unit with the least amount of sig digs. Let's take a look back at our formula, and we see that our V1 has the least amount of sig digs. It has 1 sig dig. Because we're doing like multiplication and division, we have to round to 1 sig dig. So our answer, take a look at the next term, and it looks like our answer is going to be 3 liters. A gas at a pressure of 1 atm and a temperature of 273 degrees Kelvin occupies a volume of 10 liters. If the temperature increased to 373 degrees Kelvin, while keeping the volume constant, okay, so sorry about that. So because our volume is constant, we know that we're not going to use any formula involving volume. What will be the new pressure? So our P1, our initial pressure is 1 atm. And our initial temperature, T1, is 273 degrees Kelvin. Our P2, well, we're trying to solve for this, so that's going to be x. And our T2, well, it's increased to 373 degrees Kelvin. Now, the formula we're going to use is P1 divided by T1 equals P2 divided by T2, otherwise known as Gay-Lussac's law. Plugging this into our equation, because we already know that, we know that the temperature has to be in Kelvin, and we already have the temperatures in Kelvin, so we're all good to go. Our P1 is 1 atm divided by our T1 equals our P2, which is x, and this is going to be divided by 373 degrees Kelvin. We cross multiply, and we're going to get 373 degrees Kelvin times 1 atm equals 273 degrees Kelvin times x. Divide both sides by 273 degrees Kelvin. And you see the Kelvins cancel out. We're solving for a new pressure, and we're left with atms as our unit, which is what we want. So doing this, we're going to get x equals, and then 373 divided by 273, that's just going to be 1.366, and then a bunch of other nonsense. But round to the correct number of sig digs, and we see that this has the least amount of sig digs, and because we're doing like multiplication, we have to round to the correct number of sig digs. So we're rounding to 1 digit. Take a look at the unit next to it, and we're going to get x equals 1 as our answer, 1 atms. And I should write atms here. Don't forget to write your unit, otherwise you're going to be marked wrong because your teacher might not know what unit you're talking about. A gas sample has an initial volume of 5 liters, a pressure of 2 atms, and a temperature of 300 degrees Kelvin. Let's write this down. So, pressure of 2 and a temperature of 300. Temperature of 300. Now, if the pressure is increased to 3 atms, if our temperature is increased to 400 degrees Kelvin, what will be our final volume? Everything is changing in this problem. Nothing stays constant. And when this happens, we're going to use the combined gas law. V1, P1 times V1 divided by T1 equals P2 times V2 divided by T2. And you can see that it's basically the reason why it's called the combined gas law. Well, everything's combined from kind of Charles's law, Bose's law, and Gay-Lussac's law. Let's plug this into our equation. So we're going to get P1, which is 2 ATMs, times V1, which is 5 liters, divided by T1, which is 300 degrees Kelvin, equals to P2, 3 ATM, times V2x, and divided by our final temperature. Let's cross multiply. When we do so, we're going to get 2 ATM times 5 liters times 400 degrees Kelvin equals to 3 ATM times 300 degrees Kelvin times x. What you want to do now, you want to divide both sides by 3 ATM times 300 degrees Kelvin. 3 ATM times 300 degrees Kelvin. When you do so, everything from this side cancels out, and you can see that your ATMs cancel out and your Kelvins cancel out. Sorry about that. Our Kelvins cancel out. And because we're solving for a final volume and we're left with liters as our unit, we're good. So we're going to get x equals, and let's solve this. So it's going to be 2 times 5 liters times 400 divided by 3 times 300. And hold on, let me just plug this into my calculator real quick. So 2 times 5 times 400. And we're going to divide this by 900, or 3 times 300. And we're going to get x equals 4.44, and it continues on. Now remember, we have to round to the correct number of sigdigs, and looks like 5 liters has only 1 sigdig, and this is the least amount of sigdigs. So we're going to round our answer to 1 sigdig. Take a look at the unit next to it. It's less than 5, so we round down, and we're going to get x equals 4 liters.